So basically, this is an overview. We will not cover much about convex geometry and convex set. If we work on polyhedral set, that means linear programming, then this part is actually very important, but we don't. So we just know some basic things enough. What is important is convexity for the function, not on the set. What is a convex set? The topology of a convex set, the operation of a convex X, characterization of a convex set, and property and theorem of convex set. These are not our focus. Okay, so what's convex set? Any xy in this set S, if the line segment, I draw this symbol, is in this set S, then this is convex. This line segment means convex combination of x and y. This means all the lambda x plus 1 minus lambda y for lambda between 0 and 1. You can say, I can put, this is open interval, this is closed interval. Both are okay. In fact, if we have closed interval, then we get back x and y, and we already have this. So that's why usually we don't care about this, we care about this. That means infinitely close to x and infinitely close to y is still in S. So this is a convex, this is not, because this is not in the set. So these are the basic things. But this is not the whole story. A set is convex if this is true. But you can also have this. If I have a convex set, then any x inside the set S, for all probability measure P, that means what? Lambda x plus 1 minus lambda y is in S. What happens if I have x, y, z? Then I have alpha, beta, gamma. And alpha plus beta plus gamma is equal to 1, alpha, beta, gamma larger than 0. Then what happens if I have many points? If I have many points, then I have alpha I, xi, sum, right, inside S. This is for n point. I can take limit n go to infinity, right? Then I have this, and I call it px. Then, if this is also in S, okay, so it's wrong, so it should be in S. Then this is what? This is all the p that probability dx equal 1. Okay. For this thing, we have lots of detail. What? Measurable, integratable, blah blah blah. Okay, we don't care. But my idea is, this thing actually generalizes to this. So that's the same thing. So basically it means what? Line segment of 2 points. This is what? It's not line segment of 2 points, it's a triangle. So what is a convex set? This is a line segment of 2 points. If I have 3 points, I have the triangle inside this set, then it's convex. If I have 4 points, okay, I have this shape. And here's the thing. Any 4 points, it should be any 4 points. And then what is this shape? This shape is convex combination. Okay? So it's convex how? And then it can go to what? These are finitely many points. I can go to infinitely many points. To be more serious, this means countably infinite many. This is uncountably infinite many. That means that this thing, okay, this thing. I mean the real analysis thing. Okay, we don't care. Okay, so this is how you can tell a set is convex. This is in S. This is also in S. And then what? This is what I said. Conical how, convex how of a set is convex. Okay, so what I just said is this thing implies to this, but actually this also implies to this. What's this? Convex how? No, convex set. It also means the set is the convex combination of itself. So what is this? Any 2 points, the line is inside the set, then this set is convex. Then I just said any 3 points, the triangle is inside this set is convex. And then I just said any 4 points, their convex combination, that means this shape is inside the set, then it's convex. Then I can have the following. I have infinitely many points. Okay, imagine I have many points, then I have a convex combination of this. Okay, imagine, then this becomes this on S. Then this is what it means. So S is convex if this is true. So that's the idea. And this can be any number of points. It can be countably many, it can be uncountably many. So that's the idea. So this is why I have this. But these are detail. We don't go to the detail. And then we also have this. Okay, what is this? The projection into a subspace is also convex. So this is a set. If I am here, okay, and then what? My eyeball, I look at here, I only see this plane. Then projection of this set is this. And I only see this. Any 2 points inside this set is always here. And their line segment under the projection pi is also here. So this, the red become the blue here. This line is also convex set. So that means convex set is preserved under projection. Then if this is true, then this is convex set. I mean this is true for any projection. I'm here or I'm here. Okay. So this is the idea. Again, we don't go to the detail. So this is what I mean. Okay. A set is convex if we have S is the intersection of many half space. So what is half space? This is a space. I cut it. Then I have 2 half. So this is half space. Then what is a convex set? Is this a convex set? Yes, because this is this half space this half space and this half space. If S is convex, ZVX, now I have a bunch of S, then this is convex. Now half space is convex, and I have many of them, then this is also convex. Then if my S is intersection of half space, this is convex, so therefore this is convex because of this equality. This is what I mean here. S is convex if and only if S is the intersection of half space, and you can have infinite many of them. Okay, so here's an example. This is not a polyhedron. This is a sphere or an ellipse, but I can have a half space in this line pointing here, and then a half space in here, and then I have a half space in here. Okay, but what? How many half space I have? Uncountably many, because I have these, and I have these, and I have these. Okay, if you zoom in here, you know, it's a calculus idea. You have how many points? Many points. Okay, and then each of them have a line. And you know, circle is basically infinite polygon. That's the idea. So if I have a set that is constructed by half space, and half space is convex, and intersection of convex set is convex set, so this is also convex. This is another thing. Okay, so these are the thing. And then Minkowski sum of convex set is convex. So that means what? That means if I have two convex sets, add them in the Minkowski sum sense, is convex. For example, I talked about it last week. So triangle is a convex set. Square is a convex set. There are Minkowski sum. I write this or I write M here. Is this funny shape? Okay. This is also a convex set. This is not a convex set. This is the moon. This is a convex set. Then if we draw it, okay, it will be some banana. Okay. Imagine there's a banana. This is not a convex set. This line segment, this part is outside the set. Convex set plus convex set is convex set. And then actually there's a theorem. Minkowski sum convexified sets. Let's say I have a star. This is not convex. And I call this S. Okay. If I have S Minkowski sum, S, I have 2, so I better divide by half. Then this thing, I call it S2. Okay. This is not necessarily convex because Minkowski sum of convex set is convex. So Minkowski sum of non-convex set is possibly non-convex. But if this thing, I keep adding, so I have S number, I call it number K. And if this K go to infinity, then this thing is convex. So that means if I keep adding this thing, in the end it will be this thing. Okay, so Minkowski sum actually makes something more convex. This is a theorem. These are topology. So because we don't talk about too much about topology, that's why these are just, you know this thing exists, and that's it. We don't prove it. The idea is the limit, the n, go to infinity for this sum. Okay, I just call it S n. The distance between this S and a convex object, I call it C, is 0. Okay, and this distance is not the distance in the Euclidean space. It's distance in the topological sense. And then, so basically these are geometry, because topology is geometry. So these are basically topology things. And then what? If S is convex, then S is one connected. But the opposite is not true. This is one connected. This is not convex. If I have a convex set, this is a convex set, and then I have a convex set, these are convex set, so they are one connected. But if I have two regions, this is not one connected. What's the point here? Well, if I have to describe the solution set of an optimization problem, the solution set is a set. If it's one connected, that means the solution set have one region. But if you have two regions, of course we can say this is not convex. But the opposite is not true, okay? And then if a set is convex, then it's basically a ball. So think about it. If this is a convex set, then I can get a ball. By you imagine I blow air inside, then this becomes bigger and then become a ball. But this is not a convex set. This also gives you a ball if you blow air inside. So therefore, this is not true. But anyway, these are just simple ideas. These are just for fun. Again, we are not care about this too much. What we care is about the function, not the set. So these are some old notation. This means this is continuous. This means this is continuous up to first order derivative. This means continuous up to first order derivative, and the first order derivative is L-shape. Okay, this means second order continuity. That means you have gradient and Hessian. Okay, these two are the same. I make a mistake, but anyway. This means continuously differentiable K time, and P order is L-shape. And then these are used by Nestorov. This means convex, this means strongly convex. Okay, it will be confusing, so better just write it out. Okay, and then what the heck is this? We will talk about it soon.